Given question, find slope equation and deflection equation for cantilever beam carrying uniformly distributed load by using double integration method for first UDL over whole span, second UDL for a distance d from the fixed end, third UDL for a distance L minus d from the free end. We will find the slope equation and deflection equation in a cantilever beam carrying uniformly distributed load over a whole span of length L. If we observe the diagram, then the cantilever is fixed at end A and the uniformly distributed load W per meter is over a whole span of length L. We will first draw the free body diagram. We will consider any section XX at a distance small x from the fixed end A. So here is the end A and I will take here the section XX. Now its a distance from this fixed end A is small x. Now what is the remaining distance? If we observe the total length is L, so remaining distance is L minus x. To find out slope equation and deflection equation, we have to first find out load acting in this span. Suppose we will consider here the point C in the span BC. So how to find out the load? So we know that this uniformly distributed load is W for length of 1 meter. Now in the span BC, length is L minus x meter. So what is the load? So how to calculate this load? That is equal to W into W multiplied by L minus x divided by 1. So this is the total load. And where is the point of application of this load? So it is at the center point of the span BC. So here we will take the center point and this load, that is the magnitude of load, is W inside the bracket L minus x. Now what is the distance of the center point from this point C? So we will also show here the distance, and this distance is half of this total length L minus x, that is L minus x divided by 2. Now we will take the bending moment of this load about the section XX. So we will consider the sign convention. So if this moment is in clockwise direction, we will take the negative sign, and if moment is anti-clockwise direction, we will take the positive sign. So bending moment at section XX. So if I move the compass in the direction of this load, then there is clockwise direction. So we will take this load multiplied by distance from the section XX. So we will take W L minus x multiplied by L minus x by 2. So we will write here in short. We will also take this sign negative. So we will take minus W L minus x square by 2, and this is the equation number 1. Now we know that the formula for bending moment at any section. So it is mx is equal to ei d square y by dx square. So these two equations are same. So we will equate the right hand side. So when we equate this right hand side, then we will get this equation number 3. Now we are going to find out slope equation and deflection equation by using double integration method. So we will take the first integration, integrating on both sides. So it is equal to ei dy by dx is equal to, now this minus w by 2 constant. So we will take outside, and then L minus x bracket square. Now if x integration of x raised to n is equal to x raised to n plus 1 divided by n plus 1. So here L minus x square. So instead of n, if we take 2, then we will get L minus x cube divided by 3. And here is minus x. So we will take here minus 1, because we are going to take integration with respect to x. and here plus C1, where C1 is the constant of integration. Now we will simplify this term because this minus minus will become plus. So when we simplify this, then denominator will become 6. Now how to find out this C1? So for this C1 we will apply the boundary conditions. We know that this end A is the fixed end. So at this end, value of x, so this distance from the fixed end, so x is equal to 0. At end A, slope is also equal to 0 because it is the fixed end, and at end A, deflection is also equal to 0. Now if we observe this equation, this dy by dx is known as slope. So if we put the boundary conditions at end A, x is equal to 0, then dy by dx is also equal to 0. So these are the boundary conditions. So when we put dy by dx 0, x 0, then we will get C1 is equal to. So this term WL cube by 6, we will shift to the left hand side. So it will become minus. So C1 is equal to minus WL cube by 6. Now we will put this value in equation number 4. So this is the equation number 4. So value of C1 when we put in equation number 4, then we will get the slope equation. So I will make the bracket EI dy by dx is equal to W L minus x cube divided by 6 minus WL cube by 6. Now we will find out slope at free end B. If we observe the slope equation, then this dy by dx is known as slope, and at end B, value of x is equal to L. So in the slope equation, we will put x is equal to L. Then we will get EI, instead of dy by dx, we will write here as a theta B, because the slope at B we will measure in terms of theta. We will show in the diagram. So if this is the uniformly distributed load, and because of this load, this beam AB is getting deflected, but at end A it fixed end, so it is getting deflected about this point A, and we will show this deflection in this way. Now at end B, how to measure the slope? So it is measured in terms of theta, and it is known as theta B. So we will get EI theta B is equal to W by 6. Here L minus L. So L minus L is 0. So this whole term will become 0. Minus WL cube by 6. So we will get theta B is equal to. Theta B is equal to minus WL cube divided by 6 EI. So this is the equation so that we can find out the slope at end B. Now we will use the second integration to find out the deflection equation. So we will take the integration of on both sides of the slope equation. So it will become EIY is equal to WL minus x raised to 4 divided by 4, and here 6 already there, minus WL cube by 6x plus C2. Now here is the minus x term, so we will take here as a minus 1. Now we will simplify this. So it is this minus sign, minus WL minus x raised to 4 divided by 24 minus WL cube by 6x plus C2. Now at end A, if we observe here, value of x is equal to 0, and therefore the deflection is also equal to 0, and in this equation y is known as deflection. So value of y is equal to 0. So when we put x is equal to 0, y is equal to 0, then we will get C2 is equal to. Now here this minus w by 24 and this x is equal to 0. So here L raised to 4. So we will get C2 is equal to, because we will transfer this term to the left hand side. So this minus term will become plus. C2 is equal to WL raised to 4 by 24. Now we will put this value of C2 in the equation number 6, and we will get the deflection equation. So I will make the bracket, and it is EIY is equal to minus WL minus x raised to 4 by 24 minus WL cube by 6x plus WL raised to 4 by 24. Now we will find out deflection at end B. So this Y indicates the deflection. So instead of Y, we will write YB. And at end B, value of x is equal to L. So instead of x, we will put the L. So here we will show the deflection at end B is known as YB. So we will get the equation EIYB is equal to minus WL raised to 4 by 6 plus WL raised to 4 by 24. Now here we will take the denominator common, that is denominator 24. So here we will multiply with 4. So 4 minus 4 WL raised to 4 plus WL raised to 4, and it is minus 3 WL raised to 4 by 24 EI. Therefore, YB is equal to minus WL raised to 4 by 8 EI. So this is the equation so that we can find out the deflection at end B. Now we will find out slope equation and deflection equation for cantilever beam carrying uniformly distributed load W per meter for a distance d from the fixed end. If we observe the diagram along a section AC, load W per meter is shown, and we have to find out the slope equation and deflection equation by using double integration method. So we will first draw the free body diagram, and we will consider any section XX at a distance small x from the fixed end A. So I will show here the section XX, and its a distance from fixed end is small x. Now if we observe uniformly distributed load is along the section AC. Now what is the load in between the section XX to point C? So I will carry this point C here. Now if we observe the remaining distance in between, suppose I will consider this point is P. Then from point P to C, what is this remaining distance? So from the diagram we can say that it is d minus x, and I will show here. This distance is d minus x. Now how to calculate the total load in between P and C? So we know that this load is W for 1 meter, and this distance is d minus x. For a distance d minus x, here is the question mark. So to calculate total load, we will cross multiply. So it is equal to d minus x into W divided by 1. So this load is W d minus x, and the point of application of load is this middle point of this P to C. So we will consider here the center point, and I will show here this load which is acting in downward direction, and it is W d minus x. Now what is the distance in between P and this point of application of load? So I will show here this distance. So this distance is the center or middle point of d minus x. So this distance is d minus x divided by 2. Now we will take the bending moment about the section XX. So for the clockwise direction we will take negative sign, and for the anti-clockwise direction we will take positive sign. Now if I move the compass about section XX in the direction of this load, then it is in clockwise direction. So we will take moment with negative sign minus this load multiplied by distance. So this load is W d minus x multiplied by d minus x by 2. So how we can simplify? Minus W by 2 d minus x square. So this is the bending moment about section XX for this given diagram. Now we know that bending moment about any section is mx is equal to EI d square y by dx square. So these two equations are same. So we will equate the right hand side. So EI d square y by dx square is equal to minus W d minus x square by 2. Now we are going to use double integration method. So we will take the first integration on both sides. So if I take integration on both sides, then EI dy by dx is equal to minus w by 2 as it is. Now here how to take the integration of x raised to n? So it is x raised to n plus 1 by n plus 1. So it is d minus x cube by 3, and here is minus x, so we will take minus 1, and plus c1, where c1 is the constant of integration. Now we will apply the boundary condition. So at fixed end A, slope is equal to 0 and value of x is also equal to 0. So when we put x is equal to 0, slope, that is dy by dx, is equal to 0. So these are the boundary conditions. Then value of c1. So when we put here x is 0, here this left hand term will become 0. So this term here minus will become plus. So this term we will move to the left hand side. So again it will become minus. So minus wd cube by 6. So value of c1. Now if we put the value of c1 in the equation number 4, then we will get the slope equation. So it is EI dy by dx is equal to minus w d minus x cube divided by 6, and value of c1 is, so here minus will become plus. So plus w d minus x cube by 6 minus w d cube by 6, and I will make the bracket. So this is the slope equation. Now we will find out slope at point C. So how to find out? So if because of this load, this beam AB will be deflected in the downward direction, and I will show here the deflection. Now if we observe, the slope at C is measured in terms of angle theta C, and in this equation dy by dx is nothing but slope. So at C we will write here as a theta C. Now at C, if we observe, value of x is equal to d. So instead of x we will put d. So here d minus d is 0. So this whole term will become 0. So theta C is equal to, now EI term we will transfer to the right hand side, minus wd cube by 6 EI. So this is the slope at C. Now if we observe, there is no any load in between B and C. So this beam will remain straight. So there is no bending because of this load. So theta B is equal to theta C. Suppose if I draw at point C, here is one horizontal line. Then here this portion BC will remain straight. So this theta C is equal to theta B. So this we can write here, which is also equal to theta B. Now we will find out deflection at point C. So here this is the original position and final position. So CC dash is known as deflection YC. So how to find out? So we know that this point C is having distance d from the end A. So we have to put x is equal to d. So when we put x is equal to d, then we will get EIYC is equal to, instead of y we will write YC minus w d raised to 4 by 6, because this term will become 0, d minus d is equal to 0. So minus w d raised to 4 by 6 plus w d raised to 4 by 24. So when we equate the denominator as a 24, then we will get minus 3w d raised to 4 by 24, and we will transfer this EI term to the right hand side. Therefore YC is equal to minus wd raised to 4 by 8 EI. So this is the formula to find out deflection at point C, that is CC dash. Now we will find out deflection at point B. So I will show here the deflection. Original point is B and final point is B dash. So how to find out? So if we observe, here is the C to C dash distance is given, and this deflection is known as YC, and this B to B dash is known as YB. Now from this point C dash we will draw one horizontal line, and here is the point of intersection which is known as D. So we can say that YB is equal to BD plus DB dash. Now BD is equal to CC dash and is equal to YC, and we know that deflection at point C. Now what about dB dash? So in this triangle B dash D C dash, here is the angle theta C, because this portion B dash C dash will remain straight after the deflection. So this how we can define this dB dash. So in this triangle here is the perpendicular angle, and in this triangle DC dash B dash we can write dB dash is equal to dC dash into tan of theta C, but this theta C is very small, so tan of theta C is equal to theta C, and dC dash is equal to BC. Now what is this length BC? So if we observe the diagram, this total length is L and this length is D. So this remaining length BC is equal to L minus D. So I will show here this remaining length L minus D. So we have to take this L minus D multiplied by theta C, where theta C is the slope at point C, and we have calculated. So when we put, then dB dash is equal to L minus D multiplied by minus WD cube by 6EI. So how we can write the deflection at point B? Therefore YB is equal to BD, that is CC dash, and it is YC. So it is minus WD raised to 4 by 8EI plus dB dash. So here is minus WD cube by 6EI multiplied by L minus D. For the deflection at point B, we will take minus sign as a common term, then final equation YB is equal to minus inside the bracket WD raised to 4 by 8EI plus WD cube by 6EI into L minus D. Now this negative sign indicates that the deflection is in the downward direction, and therefore how to calculate magnitude of YB by using this bracket. Now we will understand how to calculate the parameters for the cantilever beam carrying uniformly distributed load for a distance L minus D from the free end. If we observe the diagram, there is uniformly distributed load W per meter for a span BC. Now if we observe the first two diagrams, then in the first diagram uniformly distributed load is over the whole span. In the second diagram, uniformly distributed load over a span AC. Now if we subtract the any parameter for a uniformly distributed load for span AB minus uniformly distributed load over a span AC, then we will get uniformly distributed load for a span BC. So how to calculate any parameter for the third diagram? For example, slope at point B, theta B is equal to theta B1 minus theta B2. In the same way, deflection at point B, YB is equal to YB1 minus YB2.